Okay, so first question here. How are force and motion related to one another? Um, Sometimes people seem to think that in order for motion to exist, there has to be a force, but that is just not true. Forces cause changes in motion. Okay, so again, if there's going to be an acceleration, if you want something to speed up, if you want it to slow down, if you want it to change direction, then um, an unbalanced force needs to act on an object. If you have balanced forces on, forces don't necessarily cause changes in motion. If I have an object here and it's being pulled with 10 newtons of force to the left and 10 newtons of force to the right, there will be no change because those forces are balanced. All right. The next question, is force always necessary for an object to be in motion? And the answer there is no. That's sort of outside our normal everyday experience, because for us, anytime we put an object into motion, it comes to rest because there is air resistance, or there's friction on the ground, or gravity pulls it back to the ground. So if we're on Earth, we typically need a force to keep an object going. All right. So like in space, that would be an example where you would not need a force. If I threw a baseball and that baseball was just flying through space, it would keep going. Why would it keep going? It would keep going because there's nothing keeping it from keeping going. There's no air in space to stop it. There's no gravity, assuming we're someplace really, really far away from Earth, to stop it. It's just going to keep doing what it's already doing, and there are no forces on that baseball. So here on Earth, if I go to the grocery store and I'm pushing a shopping cart, I know that if I stop pushing the shopping cart with some force, it's going to come to rest. But the reason for that is that there is a frictional force coming back on that. So I do need to keep pushing to make sure that it keeps on moving. Moving on to number 3. What does an unbalanced force do to an object's motion? An unbalanced force will change the motion of the object. So basically, again, it will cause acceleration. And what does acceleration mean? It means that it can speed up, slow down, or change direction. Number 4, how can you figure out the net force of an object if there are 2 forces on it? So this is just a vector addition question. So if I have a box and something's pushing it 20 newtons to the right and 10 newtons to the left, in this case, you would subtract. If I threw another, 10 newtons of force on this side, I would add these 2 together because they're going in the same direction, and still subtract that one because it's going the opposite direction. So like direction, you add forces together, and if they're in opposite directions, you subtract. All right, moving on. Number 5, how can you figure out the net force of an object if you know acceleration and mass? So in this situation, let's say we have an object that's accelerating at some rate, we'll say 2 meters per second, and we know that it's 10 kilograms. So the question is, how can you figure out the force? Well, the force is going to be given by Newton's second law, F equals mass times acceleration. So I'm going to multiply 10 kilograms times 2 meters per second, and that's going to give me 10 times 2 is 20, and 20 kilogram meters per second, also known as a Newton. All right, number 6. What is the net force on an object moving at a constant velocity? So constant velocity is one of those important phrases. It means a velocity that is constant. Imagine that. All right, so that means that you're not getting faster, you're not getting slower, you're not changing direction, which means that there is no net force. The net force in this case is 0. It doesn't mean there aren't forces. You might have, again, 5 newtons of force moving on an object, or pushing on an object that way, 5 newtons of force pushing that way, and the object is moving with a velocity of, 2 meters per second. Okay, so you've got those two forces aren't going to do anything. This is an example. This is like the shopping cart. This is, again, when you're walking down the aisles at the grocery store, you're pushing, friction's pushing back. If there was no pushback force here, if these forces weren't balanced, you would just keep getting faster and faster and running down the aisles, at Olympic sprinter speed. So constant velocity means you have balanced forces. Again, there's no net force, but it doesn't mean the object isn't moving. It just means it's not accelerating. We see the same thing happening when a person has reached terminal velocity, a skydiver falling to Earth. Okay, they've reached terminal velocity because the force of air resistance and the force of gravity are the same, right? The air is pushing up on that person just as hard as the Earth is pulling down on the person. They're not going to get any faster when they fall. It doesn't mean they're going to stop falling. They're not going to just start hovering there, but rather they are going to fall at a constant speed. In that case, we call that terminal velocity. Next, number 7. Why is there friction between objects? Because of the inherent texture and roughness of the surfaces. Right, so even the smoothest surface that you can think of at a microscopic level has a rough surface, and those edges catch on each other when two things move against each other. What are the different types of friction? Number 8, you've got static and you've got kinetic. Those are the two main types. This is the friction of non-moving objects. So that's actually the answer to number 9. This is the friction between your foot and the ground when you're walking on dry ground. That's static friction. Or a tire on dry ground, or an object you're trying to push and it won't move because there's so much static friction that it won't leave. Excuse me. All right. The other type here is kinetic. Kinetic friction is moving friction, and we can actually categorize that in 3 different ways. We have sliding friction, and that's between 2 objects. We've got rolling friction. This is when an object is on wheels. And we've got fluid friction. Fluid friction is the friction between, it's like air resistance and water drag. It's also the kind of friction that we change something to when we use like motor oil in a car. The parts in a car, say the piston moving inside the cylinder, if it's just 2 pieces of metal, that would be sliding friction. And if those pistons are moving, thousands of times per minute back and forth, they're going to get really hot. That's because of that sliding friction. The same way if you rub your hands together, your hands get warmer. So we put oil in there to put a fluid. A fluid is a liquid or a gas, and in this case, it's a liquid, and that decreases the friction between the cylinder and the piston, and that therefore produces less friction, which is therefore less heat. Okay, number 10. Sorry. What's the difference between mass and weight? Mass is the amount of matter. So it's how much of you there is, or how much of an object there is. If you counted every single atom and every single proton and every single neutron that made you up, add all those things together, that is your mass. That's not going to change no matter where you go. Your weight is a force. It is the pull of gravity on a mass. The pull of gravity on a mass. So again, here, that kind of leads us into number 11. Why do different planets have different gravities? Before I get there, why would I weigh different things on different planets? Well, here on Earth, gravity pulls stronger on me than the moon would pull on me. The moon only pulls on me with 1/6 as much force, and therefore I only weigh 1/6 on the moon. I didn't change. The amount of matter in me doesn't change. It's just the pull on me that changes. So then the question is, why doesn't the moon pull as hard? and it has to do with their masses and size. So more mass of a planet equals more pull of gravity. Okay, so if you went to Mars, Mars is a smaller planet than Earth. The pull of gravity on Mars is only 3 meters per second, so that's about a third of what we have. So I would weigh 80 pounds on Mars, whereas here I weigh 3 times that. If I went to the moon, it's only 1/6, so I'd weigh 40 pounds on the moon. Again, nothing about my mass changed. It's just how hard those planets can pull. And the bigger your planet is, the more it can pull. All right, number 12. How do you find an object's weight if you know its mass? To find an object's weight, you use the weight equation. F sub g, that is a force, but it's the force of gravity. So that is our weight, equals mass times gravity. Now again, g, that's the acceleration due to gravity. So it's mass times acceleration. It's just a very specific acceleration. And it's the same as, the equation is the same as this one. That's the same as Newton's second law. All right. This is for any acceleration. This is for the acceleration due to gravity. So here on Earth, that g is always 9.8. So if I knew that my mass was 100 kilograms, and I'm here on Earth, the acceleration due to gravity is 9.8 meters per second, I would then know that I weigh 980 newtons. All right, number 13, explain Newton's first law in your own words. My own words would be, things keep doing what they're already doing. Things keep doing what they're already doing unless something pushes or pulls them to change. In Newton's words, it's objects at rest tend to stay at rest, objects in motion tend to stay at motion unless some outside force acts on them. In this case, things keep doing what they're already doing. Same means the same thing. Newton's second law, in my own words, would be F equals ma. That's the equation for Newton's second law. Those aren't my own words. But what I would say is harder pushes or pulls cause more acceleration or cause more change, right? If I push harder on something, it's going to accelerate more. If I try to throw a ball harder, it should go farther. It should go faster. Hopefully that's pretty obvious. On the other hand, if an object is more massive, it will not accelerate as much. So if I take a baseball and I throw it, and I can throw it, 300 feet, and then I grab a ball of lead that's the same size, and I try to apply the same force, it's not going to go that far. So harder pushes, more acceleration, more mass means less acceleration. Okay, number 15, explain Newton's third law in your own words. All right, so this one in Newton's words are every action has an equal and opposite reaction. And so basically, this is the one where if you watched my notes, it talked about using caveman speech. So basically, if I'm sitting in a chair, what's happening to me? I'm getting pulled. There's an action force. The Earth is pulling me, F sub g. All right, so what's the reaction force? Well, if Earth pull me pull Earth. Okay, so this is where you go caveman action-reaction forces. They're all forces come in pairs, and it's always one object. It's always involves two objects. Number 16. If I pull on the Earth when the Earth is pulling on me, how come I accelerate noticeably and the Earth doesn't? All right, so Newton's third law only says the forces on each thing have to be the same. So again, here's the Earth, and here's me. All right, we both are going to get pulled the same amount. Okay, F, and I'm going to pull on the Earth just as much. F, same. Okay, the forces are the same. The effect on each object is not the same. What does force equal? It equals mass times acceleration. F equals ma. All right. Well, I have a super tiny mass compared to the Earth. The Earth has a huge mass, right? Now, in order for the F to be the same, I have to take a tiny number, that M, and multiply it by a big acceleration. And here I've got this huge M, and I'm going to multiply that by an even tinier acceleration. So one so small you can't even see it. It's still there. So the Earth's acceleration is on the order of 10 to the minus 23rd meters per second, which means basically it's zero. Okay, for all practical purposes. In reality, it's not zero, but it's so close to zero that we can't imagine it being anything but. So why do I accelerate? Because I have a small mass. Why does the Earth not accelerate? Because it has a huge mass. All right, number 17, what is inertia and what does it have to do with Newton's first law? Newton's first law, again, says that objects at rest tend to stay at rest, objects in motion tend to stay in motion. In my own words, I said things keep doing what they're already doing. Inertia is the same thing as mass. It is a measure of your mass. It's a measure of your tendency to keep doing what you're already doing. So if you have more mass, or if an object has more mass, it will keep doing what it's already doing. It will require more force to change its motion. So if I have if I'm walking along the road here and I see a little pebble, and then I see a boulder, right? I can kick the pebble and make it move, right, with a given force. If I kick that rock, that boulder is not going to move if I apply that same force to it. It's got a lot more inertia, a lot more tendency to want to keep doing what it's already doing. If I want to move that, I need a much larger force. Newton's first law is known as the law of inertia. Don't forget that. All right, number 18. What are the similarities between balanced forces and action-reaction pairs? All right, so both of them, the similarities are they are equal and opposite forces. Those are the similarities. So what's the difference? The difference is that for balanced forces, they act on one object and they cancel. Okay, no change will occur on that object. It's like two teams of tug of war being evenly matched, pulling on a rope, and it's not going anywhere. Action-reaction pairs, on the other hand, involve two objects. Okay, object one, pull on two, object two, pull on one. Those forces are equal and opposite as well. It's just each force is acting on each separate object. Those objects will move. They don't cancel each other out because they are on two separate objects. That's the key difference. One object for balanced forces, two objects for action-reaction pairs. Two objects, two forces, one object, two forces. All right, number 21, how does air resistance affect acceleration of falling objects? It slows the acceleration of falling objects. If you watch the notes, there's the video of the skydiver jumping out of the airplane, and as she's falling, her acceleration becomes less and less and less until she reaches terminal velocity. So it decreases acceleration, eventually lowering it to zero, at which point that object that's falling has reached what we call terminal velocity. All right, centripetal force, we're going to skip. Conservation of momentum, we're going to skip. We did not talk about that. It's not going to be on the test. All right, what makes a rocket go? All right, so a rocket, sometimes people think a rocket is taking gas and it's pushing it out the bottom and it's pushing it against the ground, but that's not why a rocket goes. Here's a rocket, all right, and inside the rocket, there's fuel, and there's a chamber, and it's full. When that fuel starts to burn, it creates huge explosions of gas, and there's an opening out here at the back. And basically, the rocket pushes the gas out of the rocket. So this force here is rocket push gas, all right? Well, according to Newton's third law, and if I think like a caveman, the opposite is true to make the rocket go. This is the second object. If rocket push gas, then gas push rocket. And it's throwing the gas out so forcefully here that that gas is able to push the rocket at really high speeds to get it to move out of our atmosphere and into an orbit. All right, number 25. Blank opposes the sliding motion of two surfaces that are in contact. That would be sliding friction. All right, number 26. The blank of an object is different on every planet in the solar system. That would be the weight, and that's due to the pull of gravity. All right, okay, 27. When an object moves in a circular path, the net force is called centripetal force, but you don't need to know that. Number 28. The attractive force between two objects that depends on their masses and the distance between them is called gravity. For that one, remember that the farther away you get from an object, the less and less gravity becomes. So here on Earth, I'm being pulled with an acceleration of 9.8 meters per second. If I go up to the space station, my gravity is actually 8.9, about 10% less. But if I get farther and farther and farther away, eventually I'm going to get to a point where Earth's gravity doesn't affect me very much, and I'm probably affected more by other objects in space. So the farther away you are from an object, the less gravity there is. The more mass that object has, the more gravity there is. All right, 29. Blank relates the net forces exerted on an object to its mass and acceleration. That would be Newton's second law. And number 30, what is the gravitational force exerted on an object called? That is called weight. Number 31, which explains why astronauts seem weightless in orbit. A, Earth's gravity is much less. B, the spacecraft is in free fall. C, the gravity of the Earth and Sun cancel each other out. D, the centripetal force on the shuttle balances Earth's gravity. All right, not that one. Earth's gravity is actually not that much less for astronauts in the space station. Like I said, it's only about 10% less. So that's not why. The reason is that because the spacecraft is in free fall. All right. Now, again, I don't think there's one on the test like that, so don't worry about that. 32. Which term best describes the forces on an object with a net force of 0? The net force of 0 would mean that you have balanced forces. All right, 33, which body exerts the strongest gravitational force on you? The moon, the Earth, or the sun? The answer is the Earth. You might say, well, wait a minute, the sun is 1 million times bigger than us. Why don't we, why isn't the sun the answer here? Well, the sun is also 93 million miles away. So we're much closer to the Earth and to the center of the Earth than we are to the sun. So even though the Earth is smaller, our proximity, our closeness to it takes over, and we get more gravitational pull from the Earth than we do from the sun. Number 34, which term describes the tendency of an object to resist a change in motion? That is its inertia. 35, which of the following is not a force? Okay, weight is a force. It's the force of gravity. Friction is a force. It's the force between two objects. Air resistance is a force. It's the force of the air on an object. The answer here is momentum. Momentum is not a force. You know what else isn't a force? Inertia. Inertia is also not a force. Okay, remember, a force is a push or a pull. Inertia is not a push or a pull. It's something that resists those things, but it is not. All right, and finally, 36, an object always accelerates in the same direction as which of the following? And it always goes in the same direction as the net force. If I have an object that is, there's a 20 Newton force to the left, a 10 Newton force to the right, 10 to the left, this net force here, that would be the same as just having a 10 Newton force to the right. Which way is the object going to accelerate? It has to accelerate in the same direction as that net force. Okay, so I don't really have anything else on here. I'm looking at the questions. I'm not seeing anything. So if you guys, if you have any questions, let me know. Otherwise, There will be a couple questions on conversions like we've done. And then I think there's one question on scientific method. But other than that, everything we've gone over in class, or at least digitally, that's the stuff that's going to be on the test. And it's going to be a time test. It's going to be 1 hour from when you start tomorrow at 1 o'clock.